Hello, Doc Viva. I'm Diego Cabral, and this is my highly informative lab report video, where I'm going to be demonstrating and explaining some properties of electric charge. For my first demonstration, I'm going to show you what happens when you put a charged PVC pipe next to salt and to sugar. So the first thing I'm going to do is I'm going to take my wool and my PVC pipe, and I'm going to vigorously rub it. And what's going to happen when I do this is that I'm going to transfer a negative charge to the PVC pipe. Now, I said transfer because I'm not making any charge, because charge can't be created. It can only be transferred. So after I do this, we're going to have a negative charge on the PVC pipe. So what happens when we bring it close to the salt? Well, hopefully you can see that the salt started to just come up there on the PVC pipe. I'm gonna wipe that off, and then now I'm gonna just make sure the charge is very negative, and I'm gonna do it again to the sugar, and we'll see what happens. Wow, it looks like it defies gravity, and it does, because time for the explanation. Like I said, the PVC pipe has a negative charge. So we see that when I bring it close to each of these substances, they seem to defy gravity and attach and stick to the PVC pipe. Salt and sugar, at least in these two forms, are both insulators. They're not conductors because their electrons are not free to move away from each respective proton. However, that doesn't prevent each atom from orienting itself so that when I bring the negative charge close to each particle, that the positive charge is going to be facing towards the PVC pipe for each atom inside each little grain of salt or sugar. So once I bring the negative charge close, the positive charges in each of the atoms of the salt are going to face towards the negative charge. So now we have two opposite charges which are going to attract. Once I bring the PVC pipe closer and closer, what I'm doing is decreasing the distance between the two charges. And Coulomb's law states that the electric force is going to get greater and greater as the distance decreases. So once the electric force, and only once the electric force is greater than the gravitational force, then the salt is going to fly up towards the negative charge. And it showed while I was doing it, but once the salt was close enough to the negative charge and it flew up towards the PVC pipe, we saw that it just stayed there, which makes perfect sense. Because once it's there, there's the minimal distance between the two charges, and it's only gonna fall off once the charge goes away. Here is my second experiment. What I'm going to do is I'm going to charge this PVC pipe with wool, and I'm going to bring it here. It's not an aluminum can, but it's a can nonetheless. Perhaps it's heavier than an aluminum can would be, but we will still see the desired effect. So, let us. What the heck happens when I bring it close? Let's find out. Oh my God, it moves. Come back. Come on. Like wizardry. Why did that happen? So like I said, I transferred a negative charge onto the PVC pipe. So when I bring it up to the conductive material, which is the metal in the can, I don't know what it is. When I bring it close to the conductive material, the electrons are free to move inside the system. So the electrons move away from the negative charge, and what's left is a positive charge close over here. On this side, the electrons over here. So with the positive charge over here and the negative charge right next to it, it's going to pull the can forward because opposite charges attract. On to the next experiment. Now it's time for my second demonstration, which is going to make use of this homemade electroscope. It's made of a glass jar, a plastic lid that's fitted with an aluminum foil ball connected to a rod connected to two little danglies that are going to be placed inside the glass jar. So let's see what happens when I bring a negative charge up towards the ball of the electroscope. I'm going to bring it pretty close, and as you can see, when I bring it close, the two danglies spread apart, and when I bring it away, they come back together. Now the question is, what's going on here? And I've got the answer. So, when I bring the negative charge to the top, it's coming close to the aluminum foil ball. Now, aluminum foil is a great conductor, which means that the electrons inside the material are able to move freely around. So, what's going to happen when I bring the negative charge close is that the electrons are actually going to travel down because I have a negative charge up at the top. So the electrons, which are negatively charged, are going to want to go downwards. So as the electrons traverse the contraption, it's going to go down all the way to the very light danglies. And so they're going to travel all the way down to the danglies, okay? But once the danglies have the negative charge, the net negative charge, they're going to spread apart. Because they're close to each other and they both have the same charge, they're going to repel. So now we can try something else. We can charge up the PVC pipe again. I'm going to bring it close, and then I'm going to use my finger to ground the aluminum. So the same thing's going to happen. I bring it close, and they're going to spread apart. But what happens when I put my finger on it? And then I take it away, and then I take it away. Boom. It worked. I'm going to describe what just happened, and then I'm going to explain it. When I brought the PVC pipe close, just like before, the two danglies spread apart. This time, instead of taking it away and seeing them come back together, I brought my finger and I grounded it, and suddenly the danglies came together. Then I took away the negative charge, and suddenly the danglies spread open again. Now I'm going to explain why that occurred. This part of the experiment demonstrated charging by induction. So when I brought the PVC pipe, which has a negative charge close, the negative charge built up in towards the bottom of the danglies, which spread them apart because they have the same charge. Then I used my finger as a ground, and as a ground, since the negative charge from the PVC pipe is basically acting as a bully, and it tells the electrons, get out of here, I don't want you here. So I use my finger as a saving grace, and the electrons can freely just get out of there. So now there's no net negative charge at the bottom because the net negative charge went through me and out of the system. So after I grounded the system, the electrons in the aluminum foil, which were once being bullied by the PVC pipe and told to go away, could escape. And so what's left are just atoms towards the bottom of the dangly that are paired with a proton and an electron. So that's a neutral charge, which is why the danglies are no longer spreading apart from each other. However, once I take away the PVC pipe, what's left is a net positive charge because the electrons which the PVC pipe bullied away escaped through my fingers, leaving protons without an electron. So once I take away the negative charge and all the charges are allowed to fully dispense, we're left with a net positive charge, which allows the two danglies to spread apart, just how it occurred when it seemed like there was a net negative charge during the first part of the electroscope experiment. Something to note on the electroscope. We can devise a test to determine the polarity of the electroscope once I've grounded it. I'm going to demonstrate this testing method, and then I'm going to explain it I can't talk while I'm doing it because it's fairly time sensitive and you won't be able to see the effect unless I nailed the steps properly. So just watch and then you'll learn. Doc Viva states that we can assume that the charge of the PVC pipe rubbed with wool is negative, while the glass rod rubbed with silk is positive. Under that assumption, everything that I said previously is still going to follow through. Negative charge, spread apart, ground it, bring it apart, they spread apart. Boom, perfect. Quickly. Positive charge, attract the electrons, it spreads apart. You can see it? You can see it. Perfect. Now, what the hell just happened there? Well, I've got the answer. When I brought the PVC pipe negatively charged, I brought it towards the top, bringing a net positive charge towards the bottom, spreading apart the danglies. Then I ground it. The electrons, forced away by the negative charge, are going to travel through me, the ground, and escape the system. So, once I take away the negatively charged PVC pipe, which at that point is keeping the electrons towards the bottom and resulting in a neutral charge towards the bottom, once I take it away, the electrons are free to move once again throughout the whole aluminum foil, but this time there's simply less of them, which results in a net positive charge towards the bottom. So, after I charge the glass rod with the silk, bringing a positive charge, and I bring it towards the top of the aluminum foil, we saw that even though the danglies were a little spread apart, they spread even more far apart after I brought the positive charge towards the aluminum foil. So if we're asking ourselves, after I ground it, what is the polarity of the system? Well, we know, because after I bring the positive charge, attracting the electrons, it spread out even further. And I brought a positive charge, leaving a net positive charge towards the bottom. This is contrary to the beginning stage when I brought the negative charge, which forced the negative charge towards the bottom, which caused it to separate. Because after I grounded it, there was a lack of electrons throughout the system, resulting in not just a net positive charge at the bottom, but a net positive charge throughout. So, after I attract all the remaining electrons, which once again are less than what we started with, the electrons that are kind of dispersed evenly throughout, they're all going to come towards the top because they're attracted to the positive charge, leaving a completely net positive charge, not completely, but mostly negative charge towards the bottom. So that's how we know that after I ground it, there is a net positive charge. Welcome to my last demonstration. This is going to involve my homemade electrophorus. So the electrophorus consists of an insulating base, a conducting plate, and an insulating handle. And also, for the purposes of the demonstration, we have a light bulb attached. Now let me demonstrate how the electrophorus works. The first thing I'm going to do is I'm going to vigorously rub the styrofoam. And this is going to transfer a negative charge onto the styrofoam. Now that that's done, we can place the electrophorus onto the insulator, which now has a negative charge. So what's happening right now? The electrons, which are free to move inside of the aluminum foil base, are going to be repelled by the negatively charged styrofoam base. So what's going to happen when I ground the wire? Let's turn off the lights. Let's see. Boom, it flickered. If we lift it off a few inches and then we ground it again, boom, it flickered. And I heard it. but mostly I saw it. If you bring it back down, boom, flickers. Bring it back up, once again it flickers, and it makes a little sound. Let's turn off the other lights and get an even better look at the light. Set it back on the base, ground, flicker. Bring it up, ground it, flicker. Amazing. So now the question is, why can we repetitively and almost seemingly perpetually bring that light bulb to flicker? I've got the answer for you. Now, like I said, with the wool, I rubbed the surface of the styrofoam vigorously, which transferred a negative charge to the surface of the styrofoam. Now, when I bring the aluminum foil base onto it, the electrons in the aluminum are free to move as the material is a conductor. So the electrons are going to want to move away from the surface of the styrofoam. Basically, they want to be as far away from the styrofoam as possible because, as we know, like charges repel. So what happens when I bring my finger and touch the other side of the light? Well, the light acts as a bridge for the electrons to go through me and away from the styrofoam, which is negatively charged. So basically, they're, once again, using my finger as an escape and traveling away from the styrofoam. Now, when the electrons move through the light bulb, it does a little flicker. So after I grounded the wire, the electrons that wanted to escape the styrofoam are able to escape. What's left is a net positive charge inside the aluminum foil. So once I raise it from the negatively charged styrofoam, electrons are free to join as they please, and they want to because these are positively charged aluminum foil atoms. And so when I bring my finger close to it and I ground the system, the electrons from myself are going to transfer and fill every spot that the protons wanted an electron at. Because, as we know, opposite charges attract. And as I ground it, the electrons are going to pass through the light again and cause it to flicker. Now, as long as the styrofoam is still negatively charged, it's going to keep propelling the electrons away from it. So now that it's back on the negatively charged surface, the electrons in the aluminum foil want to get away. Which is why, once again, when I use my finger to ground the wire, the electrons are going to pass through and use me as ground and go away. Because they want to be as far away from the negatively charged styrofoam as possible. And as the electrons move through, the light bulb is going to flicker. So what's left is a positively charged aluminum foil. So when I raise it away from the negative charge and I grounded it once again, the electrons from inside of me are going to come through and fill every vacant spot on the aluminum foil. And as they pass through, it's going to flicker. And I could keep repeating this as long as I want, and as long as there's a negative charge on the styrofoam, which is going to repel the electrons in the aluminum. And that's how the electroforce works. I'm going to now showcase my last experiment with the electroforce. I'm first going to follow the steps of the procedure and then I'll discuss. So here I have my insulating base, and I also have some small scraps of paper and some sprinklings of styrofoam. So the first thing I'm going to do is I'm going to give a negative charge to the styrofoam. Following the steps of the procedure, after I charge it, after I charge the base, I'm going to place the aluminum foil on the insulated negatively charged base. I'm going to ground it. We see the flicker. Release my finger. Now I'm going to lift up the aluminum foil and hover it over these small scraps, and we're going to observe what happens. So I can already see there are some scraps of paper that are drawn towards the aluminum base. So I'm going to place it back on there, and I'm going to... At this point, it's worthy to note that when I ground the wire, that the light flickers. And this was after I hovered the aluminum plate over the pieces of paper and styrofoam. Because the light flashed, this must mean that at some point during the process, electrons were regained in the aluminum foil. When I first placed the aluminum onto the styrofoam and grounded the aluminum, the electrons that wanted to escape away from the styrofoam were able to leave through the ground. Then, with a net positive plate, I was able to levitate the pieces of paper. Then, after placing it back onto the styrofoam, we saw that the light flashed after grounding it. If no electrons were regained during the process, then after I placed it back onto the styrofoam and attempted to ground it again, there should have been no electrons able to leave because there were none regained. But because the light flashed, that means that electrons must have been regained at some point in the process. And now I'm gonna hover it over once again, and we'll see what happens. So yeah, I see some movement towards the aluminum foil from the pieces of paper. Now it says we place it back on there, and we can repeat steps 3 and 4, which state to ground it, lift it up, ground it, place back, ground it, and now we can hover over again. We'll see. Yeah, stuff is sticking up. It seems. I kind of blew air on it that one time. So it seems as if we can just keep repeating those steps, and the paper is always attracted. As long as the styrofoam base has a negative charge, the electrons inside the conductive aluminum foil are going to want to leave. So once I ground it, the electrons leave through the ground, and what's left on the aluminum foil is a net positive charge. So when I bring the aluminum foil close to the papers and styrofoam, we see that they're attracted because the net positive charge from the aluminum foil is attracting the electrons inside these small particles.